All right, in this video, we're going to introduce the concepts of circulation and flux for a vector field over a closed curve. And a closed curve is just a path that, well, closes in on itself, or put another way, the initial and terminal points coincide. Okay, so we'll define the circulation of our field as we move along this closed curve here, C, to just be the line integral of our field over that curve. Okay, so as we've been discussing, this is just a measure of how much the field points in the direction of motion along C, right? So as I move along this path, I've included this unit tangent vector here in red, and this dot product F dot T is just measuring the tangential component of our field at these various points along our path. And this integral is just summing up all those tangential components. Okay, now I've also written the line integral in this notation we introduced in an earlier video. So p dx plus q dy here. Now p and q are just the components of our field F. And I've written it this way in part just to highlight how circulation is related and yet different from this next concept that we're going to introduce known as the flux. Now here we're going to discuss flux just for two-dimensional vector fields. This definition for circulation above, this is valid for both two and three-dimensional vector fields. The flux for a three-dimensional vector field is not something we'll see until we look at surface integrals later in the chapter. But for a two-dimensional vector field, okay, the idea is instead of measuring the tangential components as we move along the path, we're going to measure the normal components of our field as we move along the path. Okay, so the flux here is going to be a measure of how much our field F points in the direction normal to the direction of motion along C. Okay, so you'll see in this, if you see in this figure, these purple vectors, right? This is the unit normal vector as we move along our path C. And notice I have made a choice here. So if I'm looking at the unit tangent, there's really two vectors I could consider for this unit normal, this outward pointing normal or the inward pointing normal. And our book takes the convention that if we were to say move along this path counterclockwise, then we're going to choose n to be the outward pointing normal as we move along that curve. Okay, so if I write the unit tangent in component form as x prime y prime over its magnitude, right, that's just the derivative vector, then the outward pointing normal can be found by just swapping the components for t. So you have y prime now and x prime, and then sticking a negative in front of x prime. Okay, so the dot product of these two vectors is 0, and n here will point outwards as we move along the path counterclockwise. Okay, now when you go ahead and take the dot product of your force vector and this unit normal vector, okay, you're going to wind up getting now p dy minus q dx as opposed to the p dx plus q dy. But that makes sense just given how we're constructing this unit normal vector here, right? By just swapping the components and then sticking a negative in front of the x prime. Okay, so on the worksheet, I do make this little note here that I think does help in thinking about circulation and flux. And so I say that it helps to think about the field as describing the flow of a fluid throughout some region. Okay, and the circulation then is a measure of how much the fluid flows in a tangential direction to C. So in other words, how much flow is along this path C, whereas the flux is a measure of how much the fluid flows in the normal direction of C. So in other words, how much flow is across this curve C. Okay, so in the next few videos, we will go ahead and compute some circulation and flux integrals, and I will see you there. Thanks.